Now let's skip over a couple of sections on dipoles and jump straight into capacitors. Essentially what a capacitor is just two conductors that are very close but not touching. So you can kind of picture just two parallel plates that are separated by some distance d but not touching. This configuration has the ability to store charge on there. So I could get some positive charge over here, and I could get some negative charge over there. Now, if I were to take this guy up and stick an insulator in it, and then so kind of picture me stuffing some insulator in here, and then just kind of rolling it up, it's going to look similar to this type of capacitor right here. In the real world, all the capacitors are going to tend to kind of look like that, because we're going to be looking at little cylindrical objects. Not going to see this fairly often, but it's the easiest type of capacitor to talk about. Now what happens if we hook a capacitor up to a potential source, also known as a battery? So a battery is going to supply us with some potential, supply us with some voltage, as I talked about in the first half of this chapter. Well, what's going to happen is if you kind of picture hooking it up to a 12-volt battery, and we'll say this is the positive side of the battery, this is the negative side, then this plate of the capacitor is going to get some positive charge on it. It's going to slowly build up until it reaches some charge Q, and we're going to get the negative Q set up on this plate over here. What this kind of looks like in a circuit diagram, get used to it because we'll be looking at circuit diagrams for the next couple of chapters, is here we have a capacitor. It's labeled by C, and it's kind of shown as two parallel plates. Our potential source is going to be two parallel plates as well, but kind of note that this one is a little bit shorter, so it looks a little bit different. And that's kind of what a battery looks like. The short side is always going to be the negative side. The long side is going to be the positive side. Now you may be asking yourself, well, how much charge is going to build up? So, well, the amount of charge it's going to build up is going to depend on two things. It's going to depend on how much voltage is hooked up across it, and it's also going to be related to an intrinsic property of the capacitor, which is how much capacitance it has. And I'll talk about how we calculate that on the next slide. This C is called the capacitance. The unit for that is this funky unit called the farad, shown with a capital F. And you can kind of convince yourself that 1 farad is going to be 1 coulomb per volt. And I mentioned when I talked about coulombs that a coulomb is a lot of charge. So it's going to be very rare that you're going to see a 1 farad capacitor. More likely than not, you'll be talking about millifarads, or 10 to the minus 3 farads. Microfarads are 10 to the minus 6 farads, nanofarads 10 to the negative 9th farads, or picofarads 10 to the minus 12th farads. So kind of get used to working with some of these smaller units here when we talk about capacitors. So as I mentioned on the last slide, the capacitance is a property of the capacitor and does not depend on the voltage. Really, it's a matter of geometry and materials inside of the capacitor. For a parallel plate capacitor that's filled with air, the capacitance right here, which is again going to be measured in farads, is going to be equal to the permeability of free space, remember that 8.85 times 10 to the negative 12th, multiplied by the surface area of the plates, so kind of a length multiplied by a width, and then the distance of separation squared, or distance of separation, so how far apart are these two plates. You can kind of see that either decreasing the distance or increasing the area, both of which are going to increase the capacitance, which is generally what we want to do. One way to increase the area is to kind of wrap it up like that, and you can kind of see that we can get a lot of area in just a very tiny space. So kind of coming back to the circuit that we initially had, where we had a capacitor, so of some capacitance C and a 12-volt battery. What we could kind of do is say, hey, if we know that the capacitance is going to be, say, 5 microfarads, we could ask ourselves how much charge is stored. Remember, charge is capacitance multiplied by voltage, so that's going to be 5 times 10 to the negative 6 farads multiplied by 12 volts, and that's going to be essentially 60 times 10 to the minus 6 coulombs. So that's kind of how we can figure out how much charge is on each of those two plates. This would be positive charge, that would be kind of a negative charge. Now what's going to happen if we go ahead and we take an insulator and we stuff it in between these two parallel plates? Turns out we're just going to give that insulator a special name. We're going to call it a dielectric, and it's going to be characterized by some constant that depends on the material, and this constant is always going to be larger than 1. The effect that this is going to have on the capacitance is simply it's going to be multiplied by this dielectric constant. So it's going to be the same thing, permeability, free space, area, distance of separation, but now we have just that dielectric constant. Sometimes you may even see the capacitance is going to be equal to the dielectric constant multiplied by the capacitance with just air inside. So kind of the equation from the last slide. We can just go ahead and look up some of these dielectric constants. So this K value for several different materials in this table of your book. For example, I said that air-filled capacitor, essentially we treat it like it's in a vacuum, so the dielectric constant is just going to be 1. We want to take a look at paper, we'd say 3.7. We want to look at oil, we could talk about 4, and kind of so on and so forth. Something else that's kind of interesting in this table is we have the dielectric strength, which is essentially going to be the electric field at which this material is going to break down, and we can start to have potential gapping across it. So remember, potential is going to be, or electric field is going to be the potential divided by the distance. So field strength of volts per meter. You can kind of see air, it's going to break down at a huge electric field. What that really means is the potential when we see, say, lightning, has got to be really, really, really large. Now let's kind of take a look on a molecular level what happens when a dielectric is inserted. So here we kind of have a capacitor with our electric field going in that direction right there. Now suppose we say, hey, I'm going to keep my electric field the same here, insert my dielectric. Well, that's going to orient these molecules preferentially such that the positives are going to flee away from the positive, the negatives are going to be attracted to the positive, and kind of the same over here. The positives are attracted to the negative side, and the negatives are repulsed from that side. So we've kind of polarized the material inside of there, and kind of what we're left with is some electric fields due to the dielectric that's going to oppose the electric field of the capacitor. What that's going to do is that's going to essentially lower that electric field right there. So the electric field inside of this capacitor is going to be lower. Now we know that potential is going to be equal to electric field multiplied by distance. We also know that charge is going to be equal to the capacitance multiplied by the voltage. So in order to keep the same amount of charge on this guy, positive Q and negative Q, well, here we have the electric field going down, so the potential is going to go down. If this potential goes down, I want to keep the amount of charge the same, so this is going to be equal to a constant, so that's just going to be some number, and this capacitance must correspondingly go up. So that's kind of on a molecular level why the capacitance is going to go up when we insert a dielectric in there. Now very often we say I'm going to hold this potential to be equal to some constant, and now inserting the dielectric has increased the capacitance, and so this guy right here is just going to be some number. Let's just say it's going to be 12 volts. So what the end effect at the end of the day is increasing this capacitance also means I can increase the charge that I can store on a capacitor simply by inserting this dielectric material. Now the last property I want to talk about for capacitors is that they actually store electrical energy, and it's actually going to store the electrical energy in the electric field. We can say that the energy stored is going to be equal to the work that was done to charge the capacitor. So if I say suddenly hooked up a capacitor shown in this circuit right down here, and what's going to happen is we're going to get charge build up. The amount of work that was done to put that charge here and here, to separate that charge out, is going to be the energy that's stored. And again, the energy stored is going to be in the electric field. I could then even potentially say, hey, I can disconnect this battery, and there's still going to be some energy in this capacitor. Now I could say, use this to actually charge another capacitor or something like that. So there's energy stored in that field right there. We can write this amount of potential energy in several different ways, and I highly recommend that you at least flag all of these guys, because they can all be useful depending on what you know. If you're given a problem where, say, you're holding charge constant, you want to use either that one or that one. If you're given a problem where your say voltage is constant, you might want to use that one or that one. And lastly, if you're given a problem where you see something about capacitance being constant, you want to use that one or that one. Really, they're all the same equations. You can start with that one and say Q is equal to C multiplied by V and derive either one of those two, or you can just write them all down and save yourself the trouble. Kind of the last concept for capacitors storing electrical energies, we could talk about the energy density that a capacitor stored, which is really just the energy per unit volume. And kind of the interesting thing about the energy density is it depends only on the permeability of free space and the electric field squared. One thing to kind of keep in mind when we're dealing with capacitors is we can be dealing with a lot of electrical energy. And when these capacitors are charged, their discharge can actually be extremely painful. I know, I've been shocked by capacitors, or even fatal if it's enough current going through your heart. Keep in mind that if you ever open up some electronics, that capacitors can store their charge indefinitely, store their energy indefinitely, even after you disconnect them from a power source, like I showed on the last slide. So if you ever have to open something up and you're fiddling around with you see a capacitor, make sure you take a screwdriver and just cross it across the two terminals to discharge the capacitor. They are not to be taken lightly, let's just say. While capacitors can be dangerous, they can also be very useful. If you consider a heart defibrillator to give a sudden jolt to a heart to try to steady up its beat, then really, you see the technician putting on two plates on a chest. The sudden quick discharge actually comes from a capacitor. If you look on the internet, one of the first things that comes up is this defibrillator toaster, which makes me wonder what sort of strange person created it. Now, one use of capacitors is going to be in these old school cathode ray tube televisions, kind of like your grandparents may have before the invention of flat screens. Essentially, we just had let's just say, just an electron gun that's going to fire electrons down a screen. This is going to be the front of a screen right here that's going to fluoresce when an electron hits it. If I wanted to steer that electron, then what I would do is I would say, hey, well, let me just get some horizontal plates and put a voltage across them. Get some vertical plates and put a voltage across them. So I'm kind of creating electric fields that go in that direction and in that direction. And as I change the voltage, then that's going to change the electric field. It's going to allow me to steer my beam to wherever I want on a television screen. And then what you kind of do is you vary the voltage, and you can kind of steer the beam just like in that direction right there, and you can create a nice picture. And as usual, I'll just kind of go through these summary slides and just page through them.